All right, in this second video of Unit 6, we're going to be looking at solubility equilibrium. So we're going to stick with this equilibrium idea. We're looking at reactions that are reversible, so they're going in both directions and the rates are the same. But we're going to focus more on the solubility type of reactions, so looking at precipitation reactions and more specifically the opposite of precipitation reactions. So looking at that compound and seeing whether or not it will dissociate in water and how we can determine how soluble something will be. So there are some real-world applications for solubility and soluble equilibrium. The first one is looking at sugar and salt and their ability to dissolve in water. That's all based on solubility and solubility equilibrium. The second one is a lot of times some old boilers in houses. They would use calcium sulfate, so it's less soluble in hot water than cold water, and so it allows it to be used to coat the tubes in boilers. So as the hot water is heating up, that calcium sulfate is not going to dissolve, it's not going to dissociate, and so it can be used as a good coating. And the last one is in the medical field, and so doctors will oftentimes use something like barium sulfate that has a really low solubility, so it's not going to dissociate when it's consumed. It's also safe for people to consume, and so it's a way that doctors can get pictures of the GI tracts. And so you can see this picture over here on the right of the slide is showing you a picture of that, and based on the coloring of the imaging, doctors can diagnose various different medical problems. Okay, so again, this is just looking at how we lead into aqueous solubility or aqueous equilibria. And so if we go back to just the traditional definition of what a dissociation reaction, so if we take calcium fluoride, for example, that's going to dissociate into two different ions. It dissociates into a calcium ion and then two fluorine ions. You have to remember with equilibrium that there's a possibility that the reaction could go backwards. So these calcium and fluorine ions could come together to form that solid. And once we've reached equilibrium, we can write it as a dissociation reaction using that equilibrium arrow. And so these are the types of reactions that you're going to be writing for pretty much this entire unit. So you'll have the solid and it will break into its respective ions with the equilibrium arrow in the middle. Some vocabulary that's associated with equilibrium dealing with solubility is we have to remember that solids are left out of the equilibrium expressions all the time. So your reactant, this solid that's dissociating, is never going to be in your equilibrium expression. But the aqueous products, the ions, will. And we're dealing with concentration, so always use the brackets. You're still going to take any coefficient that you have in your equation is going to be the exponent in the equilibrium expression. And now instead of dealing with Kc or Kp or just K, we're going to talk about things that are called Ksp, and so that's dealing with solubility. Ksp stands for the solubility product constant, and that's why it's Ksp, and oftentimes it's just referred to as the solubility product. And again, you will notice that the amount of solid present nor the size of the particles has absolutely no effect on the solubility at all. So let me move this up so you can see the words that are on here. So again, if you notice that the amount of solid present nor the size of the particles affect equilibrium at all, we just have to make sure there are some. If there's no solid, then obviously equilibrium can't happen. All right, so this slide is looking at different Ksp values for various compounds, and you'll notice that we have some Ksp values that are quite small. For example, this one right here for barium hydroxide is quite small, but then if you look at something like this one for silver sulfide, so you have a number that's times 10 to the negative 49th. That is incredibly small. And so as you're looking at these diagrams or this chart, you can see that your solubility product that you calculate can have a wide range of numbers. You should be able to look at a chart like this and draw some comparisons with the solubility rules. So as you think about the solubility rules and as you look at the various Ksp values, what do you think, if you look at something that is on the solubility rules, usually soluble but has some exceptions, where would that fall on this chart? Would it be something that has a relatively small Ksp value, or would it be something that has a really, really small Ksp value? So, and similarly, what's a statement that you can make about something on the solubility rules that says that it's always or most always insoluble? Would that be something over here on the left side that has a relatively low Ksp value, or would that be something on the right side here that has one of those super, super small Ksp values? Okay, and here's again some vocabulary. So when we talk about solubility, that is an equilibrium position. So remember, that can change, and equilibrium positions deals with concentrations. If you are ever looking at a question and it refers to something called the solubility product, that's an equilibrium constant, and there is one value for a particular solid at a particular temperature. So this is your Ksp values. Those are your solubility product, whereas solubility is just an equilibrium position, so that can change. Here's an example of a Ksp type of question you may be asking. So if the question says calculate the Ksp for bismuth sulfide, which has a molar solubility of 1 × 10⁻15 moles per liter, and again, this moles per liter, that's just molarity, and it's at 25 degrees. So we're going to set up an ice box just like we did last unit. So you have your dissociation reaction here. Now you don't really need the solid information, so if you want to leave this blank, that's fine, it's not needed. I just included this middle change part because that is what we got from the question. And so we're going to start with a solid, so there's no product here. Your initial concentration for the two ions is 0. The equilibrium is going to shift to the right. So your change is plus 2x for bismuth and plus 3x for sulfur, dealing with looking at the coefficients. Remember, those coefficients need to be brought down in the change box of your ice box as well. Based on the question, so it says that it has a molar solubility of 1 × 10⁻15. So the way that this relates to your ice box is that's the value of x, or that's your change here. And so we know, based on the fact that our value of x is 1 × 10⁻15, that the equilibrium concentration for bismuth is going to be 2 × 10⁻15, or 2 times your x value. And similarly for the sulfur, it's going to be 3 times 1 × 10⁻15, or 3 times 10 to the negative 15th. Remember to always write your general equilibrium expression. So Ksp is equal to the concentration of bismuth squared times the concentration of the sulfide ion cubed. And then we're just going to plug in our values that we have in our ice box, and you get the Ksp value for bismuth sulfide. And so we can see, based on this very, very small number, that bismuth sulfide is really, we would say, essentially insoluble. There is very little ions that are going to be present. So the concentration of the ions within the aqueous solution is going to be so small. So most of the solution that you have is just going to be that solid. Another type of question that I could ask you, so the previous question was trying to find the Ksp value. If I give you the Ksp value, I could then ask you to find the molar solubility. So if we remember from the last slide, molar solubility is really just the value of x. And so again, set up an ice box. You really don't need this information about your solid because solids are not included. They don't affect equilibrium at all. Start off with 0 for your initial concentration of the two ions. Figure out your x values. And then I'm just going to take my x values or my equilibrium concentrations and plug them into the general Ksp expression that I've already written. Do some basic algebra, and you get that the Ksp value of 1.4 times 10 to the negative 7th is equal to 4x cubed. And then again, do some more algebra, and you will get that the molar solubility of copper 2 iodate is 3.3 times 10 to the negative 3rd moles per liter. And molar solubility is a molarity, so again, you need to put the unit of moles per liter, or if you prefer just a capital M, that's fine. And really with these solubility equilibrium questions for right now, that's really the only two types of questions that you could ask. I could ask you to find the Ksp value, or I could ask you to find the molar solubility. There's really not very many other options of the types of questions that you will see. And then we have some basic other information that you need to know, just some conceptual ideas. So you can use the Ksp values to predict the relative solubilities of various groups of salts. So the two types of salts we're going to look at are salts that produce the same number of ions and salts that produce a different number of ions. If we look at salts that produce the same number of ions, so my examples here are silver iodide, copper 1 iodide, and calcium sulfate. All three of those produce 2 ions, a positive and a negative. And how we use the Ksp is that the solubility is directly proportional to the Ksp because each of them are going to produce 2 ions. So if you have a really large Ksp, it's going to be mostly soluble. If you have a really small Ksp, it's going to be a very low solubility. And then if we're looking at the types of salts that produce 2 differing number of ions. So I have copper 2 sulfide, silver sulfide, and bismuth sulfide. So copper 2 sulfide has 2 ions, silver sulfide has 3, and bismuth sulfide is going to have 5 ions. So there's different number of ions. When we're looking at salts that have a different number of ions, unfortunately the solubility is not directly proportional, and you have to actually go through the icebox and calculate the various solubilities and then compare them. And so you will have time in class, the next time you have class, to work on problem set 13, and I will answer any questions that you have about that. But this last 10-minute video has covered everything that you need to know relating to this particular problem set number 13.